So going back to review, what we've already covered is that a Diels-Alder reaction is also called a 2,4 cycloaddition. And the reason it is called that is because the general reaction mechanism is between a diene that has 4 pi electrons and a dienophile that contributes 2 pi electrons. And we end up forming a 6-membered ring with a double bond in between where the double bonds used to be. So that's kind of a weird way to say it, but we had our diene, that will be these 3 bonds here, and the double bonds used to be up here and down here. But since we use those electrons to go around like so, we are left with a double bond here, and that's where we get this. We're going to go in and do a whole bunch of examples and talk about the mechanism more, but I just wanted to give you the most basic possible example or definition of Diels-Alder before we get into it. So, when we talk about the diene and the dienophile, as I mentioned, the diene is going to be a conjugated diene, aka 2 double bonds that are 1 single bond apart, and it is going to be the nucleophile, and as we showed before, it must be an S-cis conformation like so. One thing that's really important that we talked about during the review, but I didn't mention last time in SI, is that since we have conformation here, we can rotate things. So let's say I have this molecule. Can it react as written? Yes or no? No, but can I just simply rotate it and react? Yes, so if I rotate that, it will turn into the S-cis. The only time we cannot rotate is, let's say I have something like that. Well, even this, you know what, let's make it spicier. So let's say I have some kind of ring formation such as this one. This will be S-trans because the double bonds are pointing opposite directions from that single bond. And so the S-trans cannot be rotated because this is locked in the ring. So this will not rotate. Last but not least, the other example where it cannot be rotated is in the case of steric hindrance, but there's only one group that we consider sterically hindered enough to stop this reaction, and I will draw it in blue so it sticks out to you guys, and it is tert-butyl. So if we have a tert-butyl on this position or this position, we will not be able to rotate. So a big X here. If it's any other group, like let's say we had this or something like that, that's not going to be a problem. We can still rotate. The only time we can't is if we have a tert-butyl such as this. And then someone had actually asked me that in the chat. Yes, sometimes if it's too bulky, we cannot rotate. The only time we consider it too bulky in this class is tert-butyl. As far as the dienophile goes, though, we know that the dienophile can be any alkene or alkyne, so any double or triple bond. And the alkene will not have a conformation, but it will have a configuration. So it can either be E or Z, or we can also call it cis and trans. And the reason this becomes important is because we have to maintain this configuration. So if our double bond looks like this, we can see that those groups are trans. And so we know that the product will be trans, like this. If it's cis, it'll end up being cis. Last thing that we covered is electron donating and withdrawing groups. And so electron donating groups are favored by the diene because the diene is a nucleophile, so it wants more electron density so it can attack better. The electron withdrawing group favors the dienophile since the dienophile is the electrophile. And the reason it's preferred is because it withdraws electrons, it pulls all the electrons to itself, and it gives the dienophile a more delta plus charge, which means that it will be more electron poor, which means it will be better at gaining electrons. And I'm just going to draw a line for you guys here because looking at my computer screen, it doesn't look like a very clear distinction between the two boxes. And I feel bad if you guys can't really see it. I know I said it kind of fast, but that was because we already covered this stuff and I want to get to reactions. Any questions, comments, or concerns before we move on? Sweet. Okay, so because there were a couple new people that came in, I'm just going to send the attendance sheet once more. So please sign in whenever you get a second. And we are going to come back to these after we do the reaction mechanism, not because these aren't important, but because we spent a lot of time on the diene versus dienophile last time. So, first reaction we are going to do is this one. I made this one up today, so it's not one of the ones above, but we will get into those as well. So first thing we are going to do is I'm going to label this A and B, and you guys are going to tell me which one is the dienophile. One person said it. B, exactly. So how do we know that B is the dienophile?
Because A is in cis conformation.
True, A is in cis conformation. Someone in the chat said electron withdrawing groups. Exactly, that's a big thing I wanted. So we know that this is an electron withdrawing group, and so is this one. What is this R group considered? An electron donating group. Exactly. This is a weak electron donating group. So I'm going to do a W electron donating group. And W just means weak. Alrighty. And so what about this OH? It's an oxygen, so it must be withdrawing, right?
I thought OH was a donating group.
Okay, and why do you think so?
Because it has lone pairs?
Exactly. So, yes, you got my trick, and a couple people in the chat did too. So, since we have these lone pairs of electrons, we donate them into the system. So, this is an electron donating group as well. Yay.
Would it be wrong to assume that, like, the first one will always be the diene and the second one will always be the dienophile, or he could, like, switch it up if he wanted to?
He could if he wanted to. I mean, in this class, he probably won't, but that wouldn't be the best way to look at it. Honestly, what I would always do is look for conjugation like this. So it's usually the easiest thing to spot. So I can see like double bond, single bond, double bond. So I know that that has to be a diene, right? And then on the other side, we see that we have a double bond. And so that's perfect. That works as a dienophile. Plus, as some people said, we have electron withdrawing groups on the dienophile, which makes sense. We have electron donating groups on the diene, which makes sense. So we are good to go.
I was wondering because I was trying to look at my notes and see where we have that molecule for electron withdrawing groups. Would it be the under, well, would it be the one that says oxygen double bonded to a carbon, bonded to an oxygen, bonded to an R group? Would the H be considered the R group?
No, because that is the ester functional group that you're talking about. This is going to just be a carbonyl. So any carbonyl is going to count as an electron withdrawing group.
Oh, okay, thank you.
You're welcome. And then someone asked about, like, what if there's electron donating and electron withdrawing on the diene, like some kind of intramolecular reaction. As far as this class goes, don't worry too much about that. You're not going to have to do like intramolecular reactions or anything like that. Just know that if we have an electron donating group, we are going to make it a better diene. If there's an electron withdrawing group, it's going to be a worse diene. So he could give you like 3 dienes, and 2 of them have electron donating group and 1 of them has a withdrawing group. Just know that the withdrawing group is going to be the slower or less efficient diene. And then someone asked, if the electron donating group was on the dienophile, would the reaction not proceed? So in this class, he's not really going to give you questions like that because it becomes sticky, because Diels-Alder is a pain in the butt when you learn about all the different stuff. Just know that if he gave you 2 dienophiles and one of them had a donating group and one of them had a withdrawing group, the one with the withdrawing group will proceed faster and it'll be more efficient. Alrighty, so I know there's already a bunch of colors on this, but I want to go ahead and remind you guys how to orient things before you react. So we always start at the open side of the diene. So the part that is open like this. One side will be 1, and then we count 2, 3. The other open one is 4, right? And as far as the dienophile goes, we just have side A and side B. And we're always going to orient 1 to A and 4 to B. And so we know that our diene is our nucleophile, so these electrons attack here to make a bond. That pushes these electrons from the dienophile to move here and make a bond. So that would then push these electrons to make this single bond into a double bond. So we can see that our original diene structure looks like this. Our original dienophile was this. And the new bonds we made, I will draw in black. So it looks like this. It looks kind of funky, but that is just a cyclohexane for now. We know that we made a double bond right here. And we also now have to put in our substituents. So we have this group. We have our OH. And just to confirm, 1, 2, 3, 4. Yes, they're on the right spots. And then we will have this and this. So I want you guys to tell me, will these aldehydes be cis or trans to one another? Exactly, yes, they will be cis. So they can either be both wedged or both dashed. And one thing I want to note is that these will not be really considered the endo and exo product. You can think of it that way. However, it doesn't really work because we're only going to think about endo and exo when we have a bridgehead, and we do not have one in this case. So yes, as someone asked in the chat, these would be both enantiomers present.
I have a question.
Yes.
Okay, so when I remember you talking about in SI about how you decide which one, like which way it should be facing, and I think it has something to do with like the double bond, or it's so like how does that work to like decide which one is better?
Yes, good question. So it's a little bit weird because the actual rules for orienting this stuff is really annoying and like has a lot of different components. But as far as this class goes, all you really have to understand is that he's usually going to give you the dienophile the way you do it. Like he's not going to make you flip things around. But he could give you the diene like this. That's ugly. Right? And so at this point, you would know that in order to react, you would have to rotate first, right? And you would rotate it so that it's open side facing your dienophile. So our double bonds are going to point this way. And like we did before, our substituents point away, like backwards. And so once you have the open side facing your reaction, so like let's say our dienophile was here, the open side is facing that. And then I always just start from the top. So 1, 2, 3, 4. If he gave it to you the other way around, like let's say he gave it like this, right? He would either give it to you with no substituents or like with the same substituent. So you know that you have to just flip it around to get this. So your open side is again facing your reaction. And you won't have to be able to tell like, is this going to be the top or is this going to be the top? Because they'll be the same or they'll be like 2 hydrogens, right? And so again, you can just start from the top. 1, 2, 3, 4.
So for the first one with the OH, like you could rotate that one. It's not too bulky. It's just a terbutyl.
Exactly.
That's bulky.
Yep.
All right.
Cool.
Another question I had, so only when we have 5 or more carbons on the diene is when we're gonna do the peaks. Because we didn't do it here.
Yes, but I wouldn't say just 5 or more. It's when you start with a ring. And the next example we do is actually going to be a ring. So, perfect segue. So, we have 2...
Rosemary?
Yes, what's up?
If your starting material contains a terbutyl, will the reaction not proceed? So, like, if you ask you that, you just put no reaction.
So let's say he gives you this, right? This definitely can proceed, right? Because it's already an S-cis. But if he gives it to you like this, you would have to rotate it in order to proceed, but you can't rotate, which means you cannot do the reaction.
Okay, thank you.
You are very welcome. That was a great question. So, I think I said the next one we're going to do rings. Yes, okay. So we have 2 examples for rings. We can either start with a 5-membered ring. This is the worst 5-membered ring I've ever drawn in my life. Or we can start with a 6-membered ring. But let's start with a 5-membered. And let's say for spiciness, I give you something fun like right? So, one thing you might be thinking first is what happened to the open side, right? Because now both sides have bonds. But I want you guys to think not in terms of substituents as much as in terms of the actual opening. So you know how, excuse me, I hiccuped. So you know how we do like the less than and greater than signs? And so it's like the alligator opening up, like that's what they taught you in like elementary school. Think of it the same exact way. So think of this as an alligator, and this is like the back of the mouth, and these are the chompers. So like those are the eyes, right? And so when it chomps towards the reaction, that's when we have it open, right? So with that alligator chomping logic, this way would be open. And so this would be 1, 2, 3, 4. And this would be A and B. So what is A always going to connect to? And what is 4 always going to connect to?
B.
Awesome. Cool. So let's draw that. Bam. Bam. We push those electrons, push these electrons, and push these electrons. And so something has to happen to this like tip, right? This carbon can't just sit here and chill in the middle of nowhere. So we're actually going to go ahead and push it up. And as someone said, form a bridgehead. So it's going to go from this to that. So it's like, I could have just done it this way. So like that. And that means I'm going to draw it in 3D, but then I'll also draw it flat for you guys because I know sometimes it's hard to see in 3D. So we have this, and I know that looks super ugly, but this is our cyclohexane that we just formed, right? The new bonds we made were this one, and our double bond here. And our bridgehead is pointing up like so. And now we have to go ahead and put in our substituents. And before I do that, someone asked if it matters that the 3D structure is pointing up or down. That's a great question. I don't know if it matters like in real life chemistry, whether it's pointing up or down, but just the convention that we draw it in is always pointing up, because then we have like a standard for our exo and our endo products. So as far as like us drawing it in this class, we're always going to draw the bridgehead going up. You're very welcome. So as I mentioned, the exo and endo product, we're going to have to figure out which one we have in this case. So I'm going to go ahead and duplicate this. So if both groups are pointing up, it would be like this. If they're both pointing down, it would be like this. Right? So if they are both pointing up, is that exo or endo? Ooh, we actually got a 50-50 split. So we're actually going to call this exo. And the way I think about it is exoskeleton is on the outside, right? So this tip is pointing outside. It's pointing exo to the 6-membered ring. And so as we can see, the substituents are pointing towards the tip, so they're pointing exo, versus when they're pointing down, they're pointing into the structure. So it's going to be endo. And
So,
oh yeah, go ahead.
so I think you said that there will never be a double bond in like the bridgehead, because some of the answer choices like show that, but that's like never an answer.
Pretty much, yeah. For this class, never the answer. And so in case anyone didn't hear what she said, if the answer he gives you ever has a double bond in the bridgehead, throw it away. In this class, we're pretty much never going to make a double bond in the bridgehead. So between these two, we're going to prefer the endo product, so that will be favored. And in pretty much every reaction that we do, the endo product will be favored. There's only a few instances where the exo is favored, but Dr. West doesn't ask about it. So I don't really cover it too much. I would if we had more time, but you don't really need it. But I will just mention that this is the case that I'm talking about. So this is the exception where the endo will be favored. And this is because we have an oxygen in the bridge.
I mean exo, because endo is always favored.
Excuse me, you're right. Exo is favored because we have an oxygen in the bridgehead, and I'm not going to cover why. Just know that there's an oxygen in the bridgehead if he asks you this, but he's never done it before, so I don't really bother. And now we are going to cover one that looks like this.
Wait, I'm sorry. You said you were gonna draw them because you drew them in 3D, but you didn't draw them in like a regular form. I drew it. I just want to make sure that I drew it correctly. Could you draw the other, the other two? Thank you so much.
I just wanted to show you guys that this is the next one we're doing because I didn't want to scroll back up. But that's a good point. Yeah. So the flat version of this would be, we have our 6-membered ring, our double bond, and then we are going to draw the favored product. So they're both going to be pointing down. And we have our bridgehead, and we usually draw it like that. So it'll look like so.
Does he usually draw them flat or 3D?
There's usually both, but most often he draws 3D. And then someone asked, wait, exo is always favored? No. Endo is always favored, except in that one case where the oxygen is in the bridgehead.
And how would the flat figure for exo look like?
It would just be wedged. So same exact thing, except these two groups would be wedged.
Oh, okay, perfect. I actually drew the bridgehead. I drew it like coming out of the ring, like in a triangle. That's fine, right?
Yeah, should be fine. As long as you understand where each thing is connected, it's fine. And so if we had a cyclohexadiene, cyclohexadiene, and I believe this is what I had given you guys. Now we do pretty much the exact same thing, except we have 2 carbons in the bridgehead. So we're going to flip this entire thing upward. So when we draw in 3D, we have this same basic shape, right? But when we go up, we go to another carbon, and then that goes down. That's ugly, so I'm going to redraw it. It'll be like so. Right? And so now, bam, we still have this double bond here. And now our substituents are going to be trans because we started with the trans product. So one is going to point up and one will point, one will point down. And the way to draw that flat will be like so. Just like before, but now it's 2 carbons instead of 1. Don't forget this double bond. And we're going to have this. And we will have the enantiomer. So we'll make this, and we will also have dashed and then wedged. So it could always be this is pointing down, this is pointing up. Doesn't matter. So in this case, can we pick a endo and exo product? No, exactly, because we're only going to pick endo and exo if they are cis. Perfect. How did you know the bridge would look like that is the question. And it's just one of those things that you kind of have to remember. So if you start out with a 5-membered ring, just know you're going to have a pointy bridge. If you start out with a 6-membered ring, you're going to have a flat bridge. And then someone asked, did I do the question with the squares yet? No, I didn't. I'm saving that for last because it is interesting, but it doesn't usually pop up on the exam. So I'll zoom out so you guys can look at the ones we've done so far. I apologize for this alligator-looking thing. It doesn't look like an alligator, but hopefully you'll remember it that way. So if we go up here, we covered that one. We also covered this one. We essentially covered this topic, so I'm not going to draw that. All you really had to know for this is that in order to do the reaction, you have to flip this so that the double bonds are pointing that way, so that the alligator is opening towards the reaction. The other thing you had to note was that this is not a dienophile because we don't have a double or triple bond. So we would have had to make this a double bond or a triple bond.
So is it no reaction?
The way it was written, yes, because it didn't have a dienophile. But if we were to add one, then it would work. But yeah, as written, no reaction. This one I decided not to go over because it doesn't usually come up on the exam, but I would like for you guys to do it just as practice. And essentially what would happen is you will just have this group be the diene, this will be the dienophile, and it will react with one another to form a bi or a tricyclic compound. So there will be 3 rings in the final product. Again, I would like you guys to try that one on your own, and it will be in the YouTube video so you guys can get the answer. So yes, the only ones we have left are this one and a triple bond example. I'm going to do the triple bond first. But real quick, someone asked, why couldn't the diene be in the benzene? Great question. So the reason, theoretically anything could happen, but it's highly unlikely. And the reason for that is because the benzene is super, super, super stable. So benzene is aromatic. Aromatic compounds do not like to react. They like their aromaticity. They don't want to ruin it for anything. So it's highly unfavorable for the benzene ring to react.
I'm sorry, and I didn't copy the part where you said why it wouldn't be endo or exo in the last example. Can you just repeat that so I can write it down?
Yeah, so they have to be cis, aka pointing the same direction to be considered endo or exo. So if they're pointing opposite directions or trans, you can't count them as endo or exo. Did you get it? I can repeat one more time if you need.
Yes, I got it. Thank you so much.
You're welcome. Alrighty, so triple bonds are not really that much fun because they're almost exactly the same as double bonds. The only difference is, let me orient this. So he can give it to you looking like this, and you already know that no matter what, your diene has to face like that. And in this case, we know that one of them is in a ring. So let's just go ahead and bam, that's ugly as heck. Sure, that's better. And our triple bond will go here. Right? And so, bam, bam, bam. We react in a circle like we did before. And so, this will have a double bond. We form our cyclohexane, aka our six-membered ring. And then we are going to have two substituents. The thing to note here is that we will end up with an extra double bond because we only get rid of one of these pi bonds. So we will be left with a double bond. Everything else works exactly the same. We just have an extra double bond. And then to clarify one more time about the last question that we covered, the reason the benzene ring won't react is because it is super, super stable. It's aromatic. So if you ever see a benzene ring, it's kind of just there to distract you. It's just going to be a substituent. It won't react.
So I wasn't paying attention. Is that what that the girl asked from? She said that's why. Like, was that the question that you?
Yes. So she said
Okay.
the benzene ring won't react, right? That's what you're asking about?
Yeah.
Yeah. So the reason it won't is because it's super stable. It's kind of just there as a distraction. And so there will be a reaction, but it's not going to be the benzene ring. So the benzene ring is just a substituent. The actual reaction will happen here. All right. So any questions about triple bonds?
I have a question.
Yes.
So why doesn't the hold on. So there's only the two double bonds are in those spaces because like that's just how it is. Like normally when we have like more double bonds in it. Normally we have like a couple of them. But like I don't know. I don't know how to phrase my question.
No, that's okay. So I think what you mean is like this diene has two, and then usually the dienophyl has one.
Yeah.
Yeah. So in all of the examples that we did, we can also have this as a triple bond instead of a double bond, and everything will be exactly the same, except you'll end up with an extra double bond in your product. So let's say this was a triple bond, you would get a double bond here.
Okay. All right. Thank you.
You're welcome.
I have two more questions about the last one we just did. I'm not too sure. First, how did you go from, the benzene ring with the allylic or looking, to the cis conformation? And then another thing is, why does the product have two substituents coming out of it?
So this, all I did was I
Yeah.
turned it a little bit.
You
So
turned
if
it.
you guys look at this, all I did was took this drawing and I turned it on its side so that the alligator was open facing the triple bond.
Oh, I see. So you kind of turned it. Yeah.
Mhm.
Okay, I see.
And you definitely don't have to do that. You could have also, excuse me, just moved the triple bond here like that. It just always makes the most sense to me. I like when everything looks the same. So I just rotated it to fit this standard that we were doing before.
Right. That makes sense. And what about the two substituents on that
Yes.
product?
So these substituents just come from this. So we have a CH3 here, a CH3 here. So they are going to be on this carbon now. And now instead of a triple bond, they're bonded to a double bond.
Oh yeah, that makes sense.
Yep. And then someone asked if I'm going to cover all these examples in the video. Yes, I am. That's why it's so long. And so last but not least, we're going to do the dimerization. And I know it's 11:54, but this is recorded. So if you guys need to leave, you can. Have a nice day. I'm just going to finish this one because it's bothering me. So when we're doing the dimerization, we are actually going to have two molecules of this square react together. So we're going to do this. And what this means is the way I've drawn it, we have the alligator open towards the dienophile, right? And so it's a weird example where the diene can also function as a dienophile. So we're going to have 1, 2, 3, 4, and it'll be like A and B. So these connect, and we end up bam, bam, bam. So we end up with a really long rectangle looking thing. And we have a double bond here and a double bond here. And I'll go ahead and highlight the diene was this part, and that translates to this. Our dienophile is this part, which translates to this. Well, and that. Let's not forget. And in blue, I'll highlight this bond that we just made and this bond that we just made.
Question.
Yes.
I see. I mean, I understand. It's a little complicated, but I understand it a little bit. However, will this be on the exam?
No. I haven't seen your exam, so I'm not sure, but he doesn't ever usually ask about this because it is super complicated and weird looking.
Great.
So it's just there if you understand the general idea of it, that's good, but and someone said when I do the exam, I'm going to hear is bam, bam, bam. I hope so. My goal is to say things in such a weird way that, like, when you're sitting in the exam, you just hear my voice tell you, like, random things. Like, that's the goal.
Rosemary, I have a quick question.
Yes.
Given that we have such a little time on this test, how do you get through these problems quickly? Like, I don't know any other way to get through these problems than to draw them all out and take a bunch of time.
Yeah. So, all I can really say is to practice them over and over and over until you get better at drawing them more quickly. But honestly, even I need to draw these out still sometimes because even though I've done a bajillion problems, like, they're hard to visualize. So what I suggest is kind of not sanction your time, like spread out your time and assign an allotted amount of time for each chapter. So if you can get through all the other kind of problems a little bit more quickly, you'll have much more time to dedicate for Diels-Alder, and then you can actually draw them out. And I know, again, that's easier said than done. But for example, let's say like you have questions like this, but then you also have reaction questions, right? Questions like this, you can get out of the way super, super fast. So let's say this one, which will be the most active dienophile, right? You can do this in like less than 30 seconds because, first of all, you're looking for a dienophile, right? A is a diene, out of the question. And then between B, C, and D, we know that the dienophile wants electron withdrawing groups. So which of these is the only one that has an electron withdrawing group? B, exactly. So boom, 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 really quick. And again, that might not have been so obvious like the first time you see it, but hopefully once you do a couple problems, like you'll be able to see that. So for these, which one?
So the
sorry. Go.
dienophile, no, it's okay. Will the dienophile always have a carbonyl group?
Not always, but that's one of the stronger withdrawing groups, so they like to have those. But like in this example, dienophile again, which is the only one that has an electron withdrawing group. And then I
have
will
a
scroll back to
question.
the other page. Yes, what's up?
He wrote something for his like chapter summary. I mean, the exam 2 summary thing. It said retrosynthesis. What's retrosynthesis?
I'll show you in 2 seconds. But one thing, people said B for this one. This has lone pairs. So it would actually donate, so that would be a donating group. So this is the only one. These are R groups. These have lone pairs. These are R groups again. And then, yeah. So those are pretty much the same.
So that in C, CN, those don't have electrons?
They have electrons, but it's a C triple bonded to a nitrogen. So the electron density won't be donated towards here. It will go towards the nitrogen. So it's going to be pulled that way, away from the double bond. Excuse me.
Wait, so you said 2 and 3 would be equal, or would they be, or 3 would be more better?
3 would be better, and the reason is 2 would be the most sucky, actually, because it has 2 really strong electron donating groups, because both of these will give electrons into the system, like so.
So would that one be the least reactive dienophile as compared to the other R groups?
Yep. So this one would be the least reactive, and then we have this one, and then this one, and then this one would be the best. And then the opposite, if we're looking for the diene, we want electron donating groups, and so we know a COH is an aldehyde. Carbonyls are withdrawing, so this one is going to suck. NO2 is also a strong electron withdrawing group, so that one's going to suck. This one just looks like that, right? So it's whatever. It's not great or bad. But here we have 2 strong donating groups. So this one is going to be really good, and that will be the best diene. And so for this last one, I want you guys to tell me which of the following cannot undergo Diels-Alder.
Question. So, do questions like these only have to do with the groups and not with like the amount of substituents?
For the most part, yes. So the only time the number of substituents really matters is like here we have 4 R groups versus 2. Or let's say we had 2 alcohols versus 1. But usually it's going to be a matter of like alcohol versus something else, you know?
Okay, so if for the one at the top, the dienophile, if 4 had 2 OHs, would 2 still be the best because it has more substituents?
So if we were comparing one like that was number 2 or one that looked just like that,
Yeah.
this one would be better actually because remember these R groups are also donating. So
Okay.
it has like this extra bad stuff. But yeah.
Okay. All right. Thank you.
You're welcome. So, yes, people caught on to like the kind of tricky part of this question. So there's only one that will actually work, and that is this one because this is stuck trans. This is stuck trans. This was the example that we covered last chapter that is aromatic. So that one will not work. This is the, wait, just kidding. This one has the tert-butyl groups, so it cannot be rotated. So C is the only one that can react. The rest of them cannot. Alrighty, so where is, okay.
The first one can't react. Sorry. The first one can't react because it's a benzene. There's 2 benzene rings, and those are only substituents.
You can think about it that way, yeah. But the better way, I guess, to think about it is just that this is an aromatic ring, and you guys technically haven't like done that one. Like you haven't learned aromaticity yet, but just be aware that this ring is aromatic because once in a while this one pops up. And so since it's aromatic, it won't react. And then someone asked, why wouldn't B react? And that is because it's stuck trans. So there's no way for you to rotate this so that it looks like this.
It's another way to think about A also that it obviously you won't be able to rotate because it's in that kind of shape.
Oh.
Yeah, but I mean,
So-
you could have theoretically, like, you know what? I'm not even going to bother saying that. It's just going to confuse people. There is a way to rotate it, but even if you rotate it, it still won't be able to react. And then Travis, you've been very patient. What was your question?
Because like on the other page when we're doing like the different forms of like Diels-Alder, like, you did a rotation with a cyclohexane with this, how should I say it, like where is it? Oh, yeah, that one.
Yes, so I'm glad you actually
Like,
brought
what's
it up.
the difference between?
Sorry.
No, I'm saying what's the difference between that one and?
Yeah, that's a great question. So I'm just going to take this and redraw it here so you can compare. And so the difference is that they're both in a ring, but one of them has an open single bond outside of the ring versus the other one is inside the ring.
Okay. All right, thanks.
You're very welcome. Okay.
That makes total sense because obviously the one outside will be able to rotate, but the one in the ring cannot.
Exactly. Yep. Okay, so I know someone asked about retrosynthesis like a billion years ago, and I hope you're still here. I'm going to go over these in the video because I don't want to give you guys like a really fast BS like explanation. the biggest thing I want to tell you guys for how to do these fast is, one, don't freak out, because these are a lot easier than what you expect them to be. They're not too terrible at all. What you have to do is essentially just like the backwards reaction. So for this one, this is what you end up with. So right off of the bat, you can tell that these are trans to one another, right? So the dienophile had to be what? Cis or trans? Trans. Awesome. And since we're left with a single bond here, not a double bond, is that going to be a double bond as the starting material or a triple bond? A double bond. Sweet. So what happened? Whatever. So it'll look like so. It doesn't matter which side is pointing up or which side is pointing to the left and which one is pointing right, as long as they're opposite. And so we know, since our double bond ended up here, we know that this little section had to be the diene, right? And we don't have any substituents there, so we know that we had a regular old diene such as this. So, ta-da! That was the retrosynthesis. And I know I said I'm not going to go over it, but I guess I'm a liar. Any questions? Oh, right. Someone said that they wanted a picture of this page. And then the other one. So, yeah.
So for the retrosynthesis, so for example, like on the test, all we do is like look at the answers and then try to do it and then see what we come up with, just for that one.
Yes. So,
all right, because that would be easier then.
Let me find an example so that you guys will believe that it's not too terrible.
Just a question. After when we're done with this session, can you go back to that example that you just did about the retrospective
Yes.
and explain it again? Thank you so much.
You are very welcome. Where is the freaking retrosynthesis? I'm gonna scream. Okay, cool. So for this one, which of the following dienes and dienophiles would create this compound, right? And so this is an example of a bridgehead one, and it's written like in 2D, right? This actually has an oxygen in the bridgehead, which is not often seen on the exam, but we already can tell that this is a what group? Donating or withdrawing? Withdrawing. So electron withdrawing groups, what the heck is wrong with me? Electron withdrawing groups are usually on the dienophile. So we're going to assume that this area is the dienophile. And more specifically, we see that we're left with a double bond. So we had to have started out with a triple bond like this. So we have a C double bonded O, OCH3. So that's our dienophile, right? And we also, if we work backwards, we know that the rest of this part will be the diene. And since there's one thing in the bridgehead, we know it's a 5-membered ring. So it will look like so, right? That's the long way to do it. But as Travis said, you could literally just look at the answer choices. And first thing is first, since we have one thing in the bridgehead, we have to have a 5-membered ring. 1 and 3 don't have a 5-membered ring, so they're immediately out. Now we're looking at 2 and 4, and they both have a 5-membered ring, but this is the diene and the dienophile. Both of these are dienophiles. We don't have a diene. So there's no way that this could be the right answer. So the only one that sort of kind of makes sense is B, right? But if you wanted to do it the long way and just double check, you do it like this, and yes, you did get the correct answer. You guys want to...
So
Go ahead. What's up?
So just to know if it's like a triple bond real quick, we just know that the other side should have like a double bond, like both sides should have a double bond.
Exactly. So if both sides have a double bond, you started with a triple bond. Yes. Do you guys want to do one more example, or should I just let you go? Because I feel like a lot of people are still here. Whatever you guys want.
Can you do the last example or not the last example, the second to last example on page 9, the last page, the retrosynthesis. Yeah.
Okay. Yes, but I just want to go over one of these exam-looking ones first.
Okay. Yeah.
Because of the answer choice thing that I was talking about.
Okay.
So, which of the following could be used in the synthesis of this, right? So you're going to have to pick one diene and one dienophile from the answer choices. And so the way to do it the fast way, the rosemary method, is the first thing you do is there's only one double bond, and you know if there's only one, then this had to come from the diene. And we can further confirm that because these R groups are weak electron donating groups. And so this is a what? Electron donating or withdrawing? Awesome. Yes, it's an electron withdrawing group because it's an ester. And we also see that there is a carbon in the bridgehead. And so by that, I know that it has to be a 5-membered ring, right? And so we know that our 5-membered ring has to be the diene because of the double bond here that we highlighted, right? So 1 is not an option. And so that gets rid of A and B. And so if we know that this is our diene, we're looking for a dienophile, and that dienophile has to be a double bond, so we get rid of the triple bond answer choice. And the correct answer is 2 and 3. You guys feel a little bit better that these are less long and hard and terrifying than it seems like they'll be? I hope so. Yay. And then someone asked where we get these problems. So most of them come from the practice problem set you guys have. I just have a spicy version. And I'm going to leave it at that. Okay. So someone wanted me to do the second to last one, I believe. If I'm wrong, just let me know. But if we're doing this one, this is actually the hardest example I gave you guys. This won't actually pop up on the exam. But...
Well, I just wanted you to actually go over the one that you just did. Like, because I didn't really catch it the first time when you explained it to us.
Okay, that's fine. But for the person who wanted me to do this one, this would take a while, and this is one of the ones that definitely won't be on the exam. So I want you to try it, and then the answer will be in the YouTube video that I post. Wow, I'm an influencer. So, okay, this one, if you wanted to do it like the other way, the longer way, which is definitely what you should do to practice, how I would go about it is we have our electron withdrawing group and our electron donating groups, and we have our double bond. So
wait, I'm sorry. I got this one, the other, like the one that you actually drew out. Like the very first one about retrospective that you
Oh,
did?
okay. Where did she go? This one?
No, like the one that you actually drew out, like the very first one of retrospective that we looked at.
This one?
Perfect. Yeah.
Okay. So, yes, what I did for this is essentially. Okay. So, we have our electron withdrawing group because it's a carbonyl, right? And we also have this double bond. That's all he really gives you to work with, right? And we know that electron withdrawing groups are characteristic of our dienophile, and the double bond is characteristic of the diene. So there's two ways to do it, right? The first way, which is what students don't usually like, but I think it makes sense, is to just draw the arrows backwards. So if we take these electrons and give it back here, right? That would mean this bond breaks and these electrons go back here. That would mean this bond breaks and those electrons go back here. So if we do it that way, we see this, right? And the green electrons made a double bond here and a double bond here. And we broke this bond and this bond. And we ended up with a double bond here. And then we have to figure out the substituents. So since they're trans, they have to be pointing opposite directions. And I didn't give myself enough room to do that, so I'm just going to move it a little bit. So one group is pointing to the right, and the other group is pointing to the left. It doesn't matter which is which as long as they are trans. And so that is the backwards arrow mechanism. That's one way of doing it. The other way of doing it involves less arrows, and it's more like conceptual, which students like more. But again, I think this is the most surefire way to do it right. But you can also think about it like the diene has to be at least 3 bonds, right? And the double bond in your final product has to be the middle, right? So we know that at least this much is our diene. So sorry about that. At least this much is our diene. And the rest of it could be from our dienophile. And, oh my gosh, I'm so sorry. And so we know that the diene has to have 2 double bonds, and the diene of the double bond in your final product is in the middle of where your double bonds used to be. So if this is where the product has a double bond, you know that the diene looked like so. We also know that if we only have a 6-membered ring with no bridgeheads or anything, our dienophile looks just plain and simple like this. And then we add whatever substituents we had. So that's the conceptual way to get the answer.
That's great. I like that way better, the conceptual way.
Most people.
And yeah, okay, great.
Okay, cool. All right. Yes, what's up?
Sorry, Rosemary, I have a quick question, but it's on chapter 12. It's like the Grignard reaction.
Okay, so I actually have to go for the tutoring appointment, but how about you send me an email and I can give you a link to the tutoring appointment, and then you can come and ask me then. Does that sound okay?
Like the one after the SI session?
Yes.
I actually can't make that one, but I can sign up for another tutor session, and then I can ask them to.
Okay, thank you. That would be great if you don't mind.
Thank you.
You're welcome.
Okay. I just wanted to ask this quick question. Is PBR3, does that change the stereochemistry or does it keep the stereochemistry?
So PBR3 by itself does an SN2 mechanism. So it
Okay.
flips. But then if you're talking about the mechanism we did in chapter 11, I think, there's 2 steps, and the second step would flip again. So overall, you maintain stereochemistry. But PBR3 by itself flips it.
Okay. All right. Because I saw both when I was looking at my notes and I was like, I don't know. Okay.
Yeah.
Thank you.
You're welcome.
Oh, just one more thing. If the answer at the end would have had 2, you see that first benzene ring? If it would have had 2 double bonds on each side of the benzene ring, it would have meant that the starting material would have been a triple bond, right?
Exactly.
Perfect. Thank you so much. You have a wonderful rest of your day.
You're very welcome. You guys too. Bye.